Alright, holiday response video on the double slit experiment thing. So, yeah, I know this isn't much of an interesting subject to people, which is sort of a commentary on just how bad things are. It's that sort of important subject in physics, in science in general even, that, these kind of things don't get resolved, and just more commentary on how silly the world is. I mean, when you think billions of dollars on a super collider, when really this is the more important information, is these premises and getting them right. And yeah, they could spend whatever, a few $1,000s to create a decent two-slit experiment, one that you could create where you could play with the variables. And that would likely tell you a lot about what the actual causes of the phenomenon are. And I do say actual causes. I don't think they have accurately defined the actual causes. So anyway, here's his reply. So he started the video with some Star Wars crap. I asked the simple question, why should it matter whether you aim the gun that fires the projectile that's going to do this magical reading of the minds thing? Yeah, he does. He posts a link to the stupid Dr. Quantum video. So I wonder if he accepts the last few minutes of that video where they talk about leaving the detectors on and not recording the results of the detectors, and the wave pattern turning back on, because human beings don't know the results, and therefore the quantum essentially reads our minds and knows that we don't know that we're watching them. And even though we have the detectors on, do you believe that actually happened, that this experiment is real? Do you? I mean, you link to it. Do you think that's credible? Anyway.
What exactly the claims of quantum mechanics are, and what exactly the issues are.
Alright, well, the claims of quantum mechanics I just think is getting dangerous right there. There's no claims in quantum mechanics. Quantum mechanics is just pointing out these probability ratios, okay, that, the mean squared and zero, or is the range of outcomes that take place when light encounters electrons. That this ratio becomes an aspect of the behavior.
It was perplexing, and very few videos discuss it. I forget how I come to this realization, that it's through all the countless lay books I've read, serious books, quantum physics, Susskind lecture series on it, Yale series on quantum, academic retreat in quantum mechanics.
Yeah, well, whatever. So again, but you're going to argue as if you have the answer, okay, that there's definitive proof of something. So I'm just arguing that I haven't seen the definitive proof of any uncertainty principle. Okay, the idea that we can't measure a photon, that I accept. We can't measure its position and its direction because of the fact that there's no small thing to measure it with. We have to measure it with something that basically squishes the photon. The photon is, what, 1,000,000 times smaller than an electron, maybe? I don't know the exact number. Incredibly small. And you're saying that you're going to rub up electrons up against it, and find out what it's made of or what it's doing. Impossible.
I've got open university books on quantum mechanics. So exactly how I come to it. But what I offer is you must never forget the claims of the two-slit experiment.
Alright, now he's saying the experiment is claiming something. I just don't understand. It's an experiment like a magic trick, like an optical illusion. And you can draw conclusions about how it's done or how it's performed. So if I watch a magician do something, I can conclude that he actually has the capacity to make pigeons. Or I can conclude that somehow he's shoved pigeons in his sleeve, and he's pulling them out of his sleeve. I mean, he's not manufacturing them in his hand. They're coming out of his clothing. There's pigeons in there. I'm not saying you're wrong. I'm just saying that I don't think you have any evidence, decisive, conclusive evidence, to justify the conclusion you're drawing, and the conclusion you're saying the experiment says is the right conclusion. The experiment doesn't say that. All there is pigeon. And I think there's a better explanation than your explanation, that, you know, quantums can read our mind.
Fall under the basic claims of quantum mechanics, and that is,
again, the basic claims of quantum mechanics are, it doesn't make claims beyond the fact that it indicates there's a probabilistic probability wave. I mean, again, the word wave comes up just because, yes, the stuff vibrating is vibrating at frequencies, so it has a wave pattern only because it has a, again, anything that moves from right to left and then back is going to have a wave. Anything that oscillates has a wave. The argument being made by me, and by, I think, could be made by others, is that first, electrons oscillate around atoms, and second, atoms themselves are oscillating inside of material. I think that's a fact, and I think that fact ought to be given some sort of recognition that you've at least accounted for it and said it can't be that.
That we have the uncertainty principle.
So again, the uncertainty principle, as first stated, was, hey, photons are really small, we have nothing small enough to bounce off of them. Everything you see because light bounces off of something. And it's not really bouncing off, right? So this is the lie. I mean, not that it's a lie, but this is the illusions that we accept in our day-to-day lives that aren't accurate. Okay, when I look outside here, I'm seeing greens and browns and all these different colors. These different colors don't exist. That's manufactured by my brain. What the photons are is red, yellow, and blue. That's what the photons are. And the photons aren't reflecting off of this stuff. The photons are being absorbed by this stuff. The electrons are being elevated in their position in orbits, and the new light is being produced in yellow, red, and green. And it's produced in amounts proportional to the chemistry of the substances. So in a sense, the formation of the shape of the atoms and the chemistry. So I mean, this is also part of a conversation we could have about even spectrometry, right? Spectrographs. You know, and the idea of this, you know, the fact that molecules do have signatures of the light they produce. And again, it's kind of significant, I think, and kind of related to this conversation. That's a little irritating. Alright, I'll be back. Yeah, wrong number of some sort. Anyway, yeah, so the uncertainty principle, we're going to have to argue this one out, and how it was established as a truth, that it's not about the difficulty of measuring photons, the smallest thing in the world, moving as fast as anything can move, and that they are saying that it's not that the photon is unmeasurable because of its smallness and because of its speed. It's unmeasurable because it's not in a position, which I say bullshit to.
And that is the reason for why we, in the experiment, set up these two slits rather close together. Such that
yeah, look, the reason why they're set close together is obviously you have to create a barrier or something, you know, so there's lots of ways to create, you know, I don't. What do you want to say? Refraction and deflections and all kinds of other harassments, interferences. But yeah, what we don't have is the experiment done with, really thin, impediment, then a little thicker, and then a little thicker, and a little thicker, to show us exactly what the difference would be. Leave everything else exactly the same in the experiment and just change the thickness of the middle barrier. And wouldn't that be enlightening? But no, we don't have that.
There is an uncertainty about whether the photon or electron passes through this one or the other.
Right, and that uncertainty is our uncertainty. How does it affect the photon? How does the photon know it's uncertain? From the photon's perspective, it went from the gun to the slit, theoretically not touching anything. Theoretically. I'm arguing that it's not theoretic because it actually did get awful close to the circle they forced it through, the pinhole, and that it got awful close to the slit material, and in interacting with these materials, that's what creates the phenomenon. But granting your theory, the photon went unmolested from the gun to whatever slit it's going through. It doesn't know it's supposed to be confused. So how is it different than the photon I would aim? How is the photon that directly goes there, because I didn't aim the gun, I'm just scattering around, know that I just scattered it around? How does the photon know I didn't aim? You're just not getting the question. How can the photon possibly be different? It's exactly the same gun. The only difference is I aim it or I don't aim it. How can there be a different phenomenon at the slit it goes through based on whether I aimed it or not? I mean, you shouldn't have to be a rocket scientist, to answer the question.
We can resolve the aim problem, and nobody claims to see any of these weird quantum effects by putting a larger separation in the slits.
Well, again, yeah, there's a difference between larger separation, so wouldn't it be nice to know exactly when the pattern disappears, when the interference, how wide does it have to get to blow it all up? I don't think you can blow it all up. You're still going to have some pattern. But let's not argue.
And, choo-choo-choo-choo through the left, choo-choo-choo through the right.
Yeah, well, they can go choo-choo-choo-choo and choo-choo-choo-choo even if it's a piece of hair in between the two slits. They could still go through A or B by just aiming. Choo-choo-choo-choo.
And no spookiness.
So, I mean, even to use the word spookiness, so you're conceding it's spooky, it's strange, it's weird. And yet your curiosity ends because somebody told you there's a principle that says photons are magical. They don't have a place in the universe. They don't obey the same cause and effect rules.
To challenge the aim is to not understand the claim. Yeah?
Yeah, well, not understand the claim. Again, it's an experiment. Experiments don't make claims. People make claims. And they use the experiment as a justification for the claim. And what I'm arguing is, no, the magician can say he made the dove, but I don't believe him. Yeah, I think there's another reason a dove popped out of his hand.
The aim of the gun, and saying, but if we can... And to understand the claim of particulate behavior and the claim of wave-like behavior.
Well, again, so you're saying it's particulate behavior, and I'm saying, okay, quite obviously, that the only way you could get this behavior is to have the photon, the particulate, interact with something. And it's the thing you're forcing it to interact with that is changing its behavior. The photon isn't doing anything different or weird. It's the substances you're forcing it to interact with that are imposing the weirdness.
And the idea of a solid or mass bestowing this particular particle-like property in substances, and the common sense notions of behaviour that are attached to those notions are defeated. Those notions are applicable no matter how far the slits are apart.
Those notions are applicable no matter. That doesn't even make any sense. But again, it's you're going to say that it's a notion of particle, and it's not a notion. Obviously, Einstein said it was a particle. He was the one that first claimed it. And Feynman and all these other guys agree it comes in clumps. It's a thing in the end. Whether it's a solid thing or not is irrelevant. It's a thing. It's a clump. It's a blob. Okay, it's not a wave.
So bringing them closer together shouldn't negate our basic intuitions about ideas of particulates and wave-like interactions. Now,
well, whatever. I don't think intuitions are anything to do with this. But again, I'm just saying, look, you're drawing a conclusion. I'm saying, where's the evidence for your conclusion? You're concluding the magic is in the photon. And you're basing it on what? You flipped a coin? I'm just saying that every one of these phenomenons is completely dependent on interaction between photons and electrons. And to claim that photons are not affected by those interactions, I think, would be kind of silly.
Inmendham suggests, and I've heard this explained or treated and negated, but
I don't know where you've heard it. It would have been nice to give me a reference of where you've heard it and where you've heard it negated.
Inmendham suggests that perhaps a slit is vibrating randomly.
Okay, I didn't suggest that, actually. I said random from our perspective. I said these exact words, I think. I said random from our perspective, not random from its perspective. I pointed out the oscillation. I pointed out the fact that it goes in a right to left kind of manner. I did draw a drawing of it. Okay, I actually drew a drawing with arrows, and I said, here's the position it's in, here's the position it's in, here's the position it's in. It's in this position twice as many times as it's in this position. So now we have this ratio existing that creates this potential for creating the doubling of the peak.
And this is the source of all interference. But I implore you to say watch the Yale lecture I'll attach, or re-watch Feynman. I've just been.
Yeah, well, I've watched the Feynman 2-slit video. Well, he's 2-hole video, right? It's not even a 2-slit video; it's a 2-hole video. Yeah, I've watched it like 5 times. And you learn something each time. You get more familiar with the terminology, and so it's good. I think the more interesting video is the one on glass. Okay, the one with the thickness of the glass, and how does the photon know where the bottom of the glass is, because it's reflecting based on how thick the glass is, and it's like, how does the photon know where the bottom surface is? But isn't that all perspective, right? The argument's being made as if the photon is looking for the bottom of the glass. The argument's not about how thick the glass is. And see, that's sort of the trick here, right? Is that, yes, surfaces are really important, but thickness is what it's really about in that scenario. And so, I mean, but you have another phenomenon, right? And this is where, Feynman uses the words, it's the mean, the average squared is where the peak goes. So if the average was 4% reflection of light, the peak now would be 16. Now, See, that's because he's not presuming the existence of a wave. He's not presuming the existence of a wave when it comes to that 4%. So there's not some pre-existing wave that's now doubled. And so that the real math now is squaring the 4%. And so isn't that interesting though? But in wave dynamics, you just double the peak. You're not squaring the mean, you're doubling the peak. Now they turn out to be the same thing, but I'm just saying, isn't that interesting how the math changes depending on whether you're thinking about waves ahead of time. There's nothing overtly wave in the glass experiment where there is overt waveness in the two-slit experiment.
Watching several videos. I've not completed the Feynman one again, but I'll attach it. I think he's one of the better explainers, but he may not deal with the issue.
No, he doesn't deal, especially doesn't deal with your Dr. Quantum animated video of the double slit experiment that you posted a link to. He certainly doesn't deal with any, well, we have the detectors on, but we're not going to read the results, and somehow the photon, okay, not only knows that we don't know, okay, it somehow the photon knows that we didn't turn the tape machine on. I mean, fuck. You think that really, again, you think that really happened? This is really bad science. Sorry. This is bad, evil science. Dr. Quantum is an evil video.
But the point is wave-like behaviour destroys any chance of registering a photon at certain points.
Wave-like behavior destroys the chance of registering a photon at certain points. But again, it's, as Feynman puts it, it's all about probability. So it's no wave-like property in the sense that it's just a probabilistic curve. Okay, this is the probability curve.
And a randomly moving slit.
Again, it's not random moving, it's oscillating. So let's change the language. I'm sorry if there was a misunderstanding. I don't think there's any excuse for a misunderstanding, because even though I did say the random from our perspective, I did say from the photon's perspective it is not random. I did say the word frequencies. I did say harmonics. I mean, it's vibrating, okay? It's not going halfway and then stopping, going halfway this way and going halfway that way and going... No, it's oscillating at a frequency.
Wouldn't account for that drop to zero probability. It doesn't give an...
Wouldn't account for the drop. Yes, it would. So here's my argument. That if the... and we can just describe this too as an electron. So if I was to say that the odds of encountering an electron are, you have the 50% odd here, and you have a 0 at this side. So if you're coming at the electron from here, you would have a 0 chance of encountering the electron if the electron's in this part of its cycle, and you'd have a you'd be twice as likely to encounter it in this half of the cycle. And again, you can just convert this to a moving atom and realize that yes, it has to go through this middle position twice as often, and that twice would be paid for by this furthest distance being a 0 and this closest position being a half.
Account of interference is the point.
Well, and again, what part of the atom this is all being created by? I can't, I don't have that certainty yet. But we have a third experiment that deals with electron spin and when the electron releases a photon, and there's clearly a power level that it has to be up to. It doesn't what's the right word? Oh, come on, digital and analog. It's not an analog system, it's kind of a digital system. It has to have the necessary amount. Well, that necessary amount could be based on the fact that there is this clock kind of mechanism, and that if it's at 3 o'clock, you're going to need 9 o'clock worth of new clock to get it all the way around to 12. So it just has to be how much more you need to get all the way around. And that always has to be more than what is necessary to get all the way around. So, if it's at 6 o'clock, you need 6 units to make a complete unit that would allow it to release a photon. So anyway, but I don't want to get into that.
And so it is if, there's no explanation. If we have two randomly moving slits, yeah?
Well, they're not randomly moving, and obviously I guess what I'm going to argue is they're going to move at a frequency that's quite dependent on the thickness of the material. So again, we're back to the glass example. The glass, depending on how thick the glass is, changes, okay, what the probabilities are. So if the glass is a certain thickness, there's no reflectivity. If it's another thickness, there's high reflectivity in terms of photons encountering the glass. So here we have a circumstance where the thickness of the glass is somehow changing how reflective the material is. And I'm arguing that that change is because of how much jiggling the atoms can do at different thicknesses. At different thicknesses, their frequency has to change. And as their frequency changes, their likelihood of influencing a photon is changed. Their position of the atoms or the whatever. Like I said, I don't have the exact dynamic. I don't have the model, but I'm just saying that obviously that movement, we can imagine that a container, if we have jumping beans just jumping, and I squish the jumping beans down, I put a ceiling above them, and now they hit the ceiling. Well, now they'll jump faster because I've reduced the length of their wave. I've forced their wave to become shorter, and now their frequency has increased. And the same thing is happening to the matter. When you make this little slit, the amount of vibration in those atoms is now being confined in a different size of material. So it's probably going to be vibrating at a different frequency than the outer edge, which is made of the same material but is much bigger, denser. So there's more freedom of movement. Possible, not possible, part of the reason, not the reason, it just doesn't matter. My point is that the movement of the atoms, I think, is the only rational excuse for why the thickness of the glass changes reflectivity, and I think the same principle could be applied to slit material.
This doesn't give any reasonable account for why we don't get photons, electrons registering at certain positions.
Yeah, it doesn't. Well, it does in the sense that, like I said, I think it does explain. What it doesn't explain is as if the classic description of how the two-slit experiment is done, where you leave everything exactly the same and you close one of the slits, and now light doesn't hit where it was hitting before. I'll agree. If that's true, then this doesn't explain it. But I don't think that's true. I think that's an optical illusion of the way they perform the experiment, and that they don't leave everything exactly the same and cover a slit, and that's a problem.
Only the idea of some kind of wave giving the constructive, deconstructive interference.
And again, we're talking about something that has the phenomenon that's only taking place in very low light conditions. So much like the pinhole camera, it only works if the hole is very small, and it's a very few photons that are being filtered. And it's a time-lapse camera actually, pretty much, right? It could take a day to get a photograph out of it. So it's filtering for a very narrow amount of the light that's being produced. And so that you have to question, well, what's the consequence of that filtering? I wanted to make some other point. Well, I can wait a little later.
Seems to reasonably give that idea.
Well, again, you didn't explain, you can say it doesn't account for, well, I'm saying you still haven't accounted for how a photon knows that I aimed it or I didn't aim it. How the hell does a photon know the difference? It's traveling through the hole to the slit, it goes to the target. How does it know it wasn't aimed?
The idea that we can place a sensor and with the faintest photon sensing off an electron,
Well, so I'm just saying you can't do that. So yeah, you could sense electrons, okay, using photons, but that's still awful dangerous. We can't measure electromagnetic spectrum elements, in my opinion, without influencing them. They're not big enough. We can look at a car and not influence it, okay, because we're seeing reflected light anyway. We didn't even produce the light. But let's say we had to shoot infrared beams from our eyes and then have it bounce back to see a car. Yeah, there'd be very little capacity for us to influence the car because it's not enough energy to influence the car. The energy of the car is like times the speed of light times the speed of light. More energy than the amount of energy I would be throwing at it. So it has a zillion times more energy, matter, substance, than the thing I'm using to detect it. That ratio is nowhere close to the ratio of throwing photons at electrons, or vice versa, or trying to see a photon's position with any instrumentality. We don't have any instrumentality that allows you to do that. There's just nothing. You're basically saying crash a Volkswagen into the Volkswagen to see where the Volkswagen is. That ain't going to work. And in the case of a photon and an electron, I think you're basically saying throw a cement block at the Volkswagen. It's still a significant influence.
Such that the power is minimal, and we don't expect to change its particulate trajectory.
Well, considering that this is all the thing has, basically, is a position and a trajectory, and that it doesn't have any other element to it, again, the very fact that you're saying you've rubbed up against its position and its trajectory enough to detect what it is, seems to me impossible for you to say I rubbed some of that information off of it without creating information. So I'm just saying I don't think it's possible.
Influence its momentum much, but we can detect it. That we have what is explained as the two-slit phenomenon, the appearance and disappearance of fringes, of interference patterns, based upon a seeming knowledge of an observer.
Yeah, well, I don't think it's any knowledge of the observer, and I don't. The fact that you've established what slit it went through, you established what slit it went through at the cost of its original trajectory, and you've basically just taken the photon that was on a direction going that way or that way or that way or that way, and now made it go this way. So yeah, that's probably the reason why detectors always fail.
The mere random...
That's why I say it's just easier just to aim the gun, and then you don't need detectors.
Randomness of slits doesn't account for that behaviour. But I can't stress enough that you can't make the issue out of aim when the claim is that the common sense notions of particles and waves and the behaviour of matter as marbles with a particular property breaks down.
So you're saying it breaks down. I'm saying it doesn't break down. Okay, you have pigeon. You're saying the guy made the pigeon. I'm saying no, it's up his sleeve. Okay, the experiment is creating the wave pattern. The photon isn't creating it.
Due to the uncertainty of these slits. So the distance between the slits is very much related to the mass or the wavelength of the photon. The uncertainty principle.
Well, yeah, that's true. So why didn't they just do the single pedestal experiment? Why did they even bother with the outside walls? Because yes, you can create a diffraction pattern by just shooting light through a impediment, and it diffracts around it. And everybody understands that, right? Yeah. And it's not called an interference pattern. It's called the light on this side gets spread this way, the light on that side gets spread that way, and they spread into each other.
Some people still try to explain it, academics even, but what's convinced me is the pure mathematical statement of the uncertainty principle.
Alright, so I don't know, this mathematical statement of the uncertainty principle I think is bogus, but fine, go ahead.
And several sources which tell me that it's nothing to do with the measurement. The uncertainty principle is taken as a fact of quantum science. Not
taken as a fact. Again, proven by what experiment? What experiment proves that the photon knows when I aim it or not? That the photon knows when I have registered and recorded its position. Somehow the photon knows that I recorded the fact that it went through slit A. Come on.
Not explained away as the observation literally interfering with the particle. The uncertainty principle is stated in a strict mathematical inequality.
It's stated as a made-up statement that, again, I'm saying that it has nothing to do with where the wave is coming from. The wave is coming from the movement of the matter you're interacting with.
And I can't remember it to state it which way it goes, but it's the uncertainty is greater than or less than, I don't know, than the momentum times position or something like that, isn't it? Yeah, but it's this statement of a mathematical fact which means that we're testing. So we can't.
Again, mathematical
engineer
facts. I mean, I don't. Where do you get that from?
Situation. So certainty is absolute. Yeah, it's predicated upon where there is uncertainty, and the claim is that things are uncertain at these distances. Okay.
The claim is that things are uncertain at these distances. Well, the claim is if you don't aim, that's true. You're not going to know, but you're definitely going to know proportions. And it still wouldn't explain why the photon itself behaves differently based on your knowledge. Your knowledge is really not relevant.
And the claim is the probabilistic nature as well.
Well, let's just stick with that idea. There's a probabilistic nature. That's right. Then the probability in the glass experiment of the reflection happening is completely dependent on the thickness of the glass. And now the only thing to figure out is, does the photon know how thick the glass is? Or is the glass forcing the photon to providing the information on its surface? Is the information of how thick the glass is available at the surface of the glass. I would say theoretically, if we understood this dynamic better, that we could tell from the frequency of the movement of the atoms how thick the glass is. And I think this explains why there's, the different sound pitches in glass and all of that kind of stuff. That these are all phenomena that are likely connected.
So I hope that answers Inmendham's question.
Yeah, no, it doesn't. I mean, how exactly did you answer the question? The photons know if they're being aimed. Okay, that's your answer. I think it's a crazy answer. So yeah, forget it. That doesn't work for me at all. Again, show me the distinction. I aim the gun, the photon goes like this. I don't aim the gun, but I shoot a variety of ways, but the photon that will make it to the slit goes exactly the same as the one I aimed. It'll be exactly the same way. It's the only way it can get to the slit because of the hole in there. So, I could aim it, or I can just randomly shoot and have it get to the same exact, it's going to end up in the same damn place whether I aim it or don't aim it. And you're saying somehow that photon knows it was aimed or not aimed. I say that's bogus. So, anyway, I think that's enough. There's probably other stuff I had thought of that I should get to, but, there's lots of details to go through here. But I'm still saying, okay, I don't think this is an answer to my question. I don't think it resolves it in any decisive way that you demonstrated to me in some decisive way that photons know whether they've been aimed or not, that they carry it on their body somewhere, on their person, in their wave function. Somehow they know they were aimed or not aimed. I don't buy it. So anyway, till next time.